Welcome to the What on Earth podcast, where we try to answer all of your "what the hell is going on" questions.
We are Tika and Veronica, and we are very happy to have you here with us today.
Today I'm taking Tika and all of you on a journey to our closest celestial neighbor, the moon. But what if I tell you that our glowing companion is nothing but peaceful? It's actually a survivor, a silent witness to the most violent chapters of our solar system's history. So grab your tea, wrap yourselves in a nice blanket, and get ready for the takeoff. So, since the cradle of human existence, the moon has played a profound role in myths and spiritual narratives across many civilizations, starting as early as ancient Mesopotamian cultures, where the Sumerian god Nun was worshipped. Across centuries, the moon became a multifaceted symbol of time, magic, and it influenced religion and agricultural calendars. It underscores its universal significance as a celestial force that shaped the spiritual and practical aspects of human societies throughout the history. But what about its scientific relevance? Why did scientists, me included, spend years studying various features of the moon? Tika, take your bet.
This is difficult for me because I'm not much of a space person. I really enjoy everything that happens on Earth, but I think that's also the reason why we study anything outside of the Earth, because it might tell us a bit more about what's happening on our home, and also maybe recently because we are not being very careful with our Earth. We are trying to find a new home, maybe.
Yeah, okay, interesting take. I mean, there is no life on moon, of course, but it definitely tells us a lot about Earth in very surprising way, because on the moon we don't have plate tectonics, so it made it possible to retain the primordial features which on Earth are erased by plate tectonics. So the moon's weathering processes, especially for the surface, are very limited, and there's only cosmic exposure, solar wind, granulation by meteorite bombardment. And assuming that due to the moon's proximity to Earth, both of these bodies were exposed to more or less the same environment, so the moon plays a vital role as an archive, some sort, of the rocky planet's early evolution. And one of the major outcomes of the Apollo mission was to discover that the moon is composed of a variety of igneous rocks that differ widely from both chemistry and mineral composition. Tika, can you make an estimated bet on how many grams or kilograms of rocks we brought to Earth via various lunar missions?
Okay, this is going to be a complicated calculation. So, how many moon visits did we do?
So we were successfully on the moon 6 times between 1969 and 1972, and 12 astronauts have walked on the lunar surface.
Okay, let's assume we have 6 travels every time. There was 1 geologist, and it
No.
was for like more?
That's actually very interesting that you mentioned that, because not every Apollo mission had a scientist on board. Because you have to remember that for a very long time, or like at the very beginning at least, the primary mission of going to the moon was just to winning a space race. So we had to be fast. Yeah. So most of the people were just military.
I forgot about the ego.
Yeah, we had to be there first. Not the most accurate. Yeah.
Okay, let's say we have like 6 geologists that's been to the moon. We just average them out for 1 per space mission. Then we have like 90 days to gather, like average length of a mission. So we have 90 days to gather rocks. If everyone gathers 1 kilogram of rocks for every day they are there, we have 6 times 90. So I would say 400 kilograms, kind of.
You're not far off with your bet, even though the estimation of how many geologists were on the moon, it was like well overshoot, but that's okay. Because, yeah, again, mostly they were just military people. But generally,
Hopeful. I'm so hopeful.
yeah, you're so hopeful. Like, you should design those missions, you know? You should design those missions
Hit
because,
me up, NASA.
yeah, or ESA.
Or
Um,
ESA.
through various missions, we actually collected 382 kilograms of
I
lunar
was only
samples.
18 kilograms off.
Yeah,
Only 18.
yeah,
Yes.
good
Wrong
estimate.
estimate. Yeah, it was a wrong method for estimating, but the result was there.
Yeah, yeah. To be fair, wrong approach, but very correct answer.
It's like the same with like the correlation doesn't mean causation.
Yeah.
Anyway.
Anyway, coming back, yeah. So we have 382 kilograms of lunar samples, and out of these lunar samples, we anyway already have quite variety of lithologies, like we know of. I will right now send you a high-resolution photo of the moon. Can you tell me 3 features which are easily spotted at the first glance?
Ooh, vibes. Okay, what did you say? 3 features.
3 features.
3 features. Okay, so first, I see a lot of round shapes, which we saw in the planet episode as well. So I'm guessing those are crater impacts again.
Ding!
Then we have larger spots. They look like round spots as well, but they seem less round. So that might be some other feature. And then there's these spiderweb white-like structures that look very interesting.
Yeah, you definitely were very correct with naming the craters. I'm very proud of you. You're becoming a space girly. And then, what is the color difference between the bigger shapes you mentioned? There's a color difference?
Well, good one. So the overall surface of the moon is lighter or more white shaded. But then the large structures, the large round structures are more blue brownish.
That's very good observation. So we have not only like cratering, but we also have color contrast, which can tell us something about chemical composition, right? Because here we have a darker spots, and then we have a whiter, brighter spots. So these are the 3 features which I will be talking about now. Because the simplest division of the lunar lithology can be made into this bright colored highland rocks and the dark basalts of the mare. And highlands can be further subdivided into 3 major units, which is like very geological division, into Ferroan anorthosites. And I'm only mentioning this because these are the rocks I worked with during my PhD. Magnesium suit and creep rocks.
Yes, so you actually worked on rocks from the moon, right? You actually got them in your lab and got to like touch them, feel them, see them.
Yes, I worked for 5 years at ETH on lunar magma ocean crystallization, which I'm not gonna talk too much into details because I want to keep it first per episode. But I did work with 16 lunar samples. Most of these samples were from Apollo 16 mission. So these samples are very well documented, and they are also the most interesting for me because I was looking into the creation of this Ferroan anorthosites and the creep rocks.
The brown spots,
the bright,
right? The larger.
The bright.
Oh, the bright ones. Okay.
Because the ferroanorthosites, or FAN, if you want to abbreviate them, FAN, they are actually the ancient crusts. So these are the oldest rocks from the moon. So if you research these ones, you kind of get window into the creation of the moon, because the mare basalts, which are the brown spots, the dark spots, are actually much younger. So the mare, like I said, are this dominant feature on the moon because they are the most contrast one. But actually they covering only 17% of the lunar sample. lunar surface, and they are only 1% of lunar crusts. And why is that so? Because, you kind of looking at the moon, you see them very vividly, but they are not on the dark side of the moon, right? Because I hope our listeners know that when we look at the moon, we only see one side of the moon always.
That still baffles me, but how do we know what's on the other side? How do we know that they're only on this or mostly on this side, and why?
Yeah, so we know how the dark side of the moon looks like because we flew around it. So we have photography, and we this is literally very striking contrast that on the far side of the moon, we don't have Mare, which are so much visible on the surface, and on the closer side, the nearer side of the moon, we actually see a lot of these Mare basalts. That's why, if you have a fast glance on the moon, it takes up much more space on the nearer side, but it doesn't take up a lot of space on the other side. And they are virtually basaltic lava flows. And these lava flows erupted during post-lunar magma ocean magmatism. So what happened? That's a lot of magma. So what happened after the moon was formed? There was an event which caused this magma to erupt and float over. It flows to the lowest point, and it was filling ancient craters and impact basins. So
is that why they look round?
That's why they look round. Exactly.
Because there's also gravity on the moon, as is on Earth.
Yes, it's not as strong, but there is definitely enough gravity. So these one just pulling down. And these lava flows are enriched in iron and titanium. That's why also they are quite dark. And besides the lava flows, Mare volcanism was also represented with various eruption of pyroclastic deposits, mainly glass.
So you were talking pyroclastic. Can you explain again what that means? Because it's a difficult word.
Yeah, pyroclastic means that it was virtually like when you have a classical eruption of volcano, Mount Vesuvius or Mount Helen, and then you have explosion which ejects a lot of material into the air, and then it creates this clouds and a lot of droplets of frozen magma. This is what we talk about pyroclastic deposits.
So the Mare, you said?
Mare.
Mare. They were only on the near side, so the side we see almost every day.
Yeah.
Can you explain why?
Yes, it's not again straightforward, and there's research to explain this dichotomy of the moon, but it can be associated to the near side has a thinner crust. So when the moon was formed, the magma ocean cooled down not evenly, and the near side ended up with a thinner crust, while the far side developed much thicker crust. And then you have these giant impacts created very deep basins, which then later on during this lava flows, they are flooded down and pulled over. That's why they are round, right? And because the near side was easier to penetrate, the lava surfaced there much easier because it was much thinner. Yeah, Tika?
Yeah, that's also why they became deeper then, right? Or bigger, or...
it's just why they reached the surface, because the crust was thinner, so they could penetrate the surface. Because there is a theory, or it's not even a theory, there are something which is called cryptomaria, and they are just like lava flows which never made it to the surface, so they are still frozen in the crust. And this is what we think happened on the far side, the one that we cannot see. And then another attribution to why we have this black spots of Mare basalts on the side we see is that during the cooling of the lunar magma ocean, you have a concentration of radioactive elements. And uranium and thorium, these are the elements which we are talking about, they have a radioactive decay. And this radioactive decay produces heat. So if you have more of these elements in the side which we see, they produce more heat. And then this extra heat helped to keep magma flowing, which is perfect condition for forming mare. So it's like you have the more basins, more craters on this side from you see, the one that you see. And then those basins were filled with the mare, and the mare could reach the surface because the crust is thinner, and it had more heat from these radioactive elements already being in the site of the moon. Is that understandable? That makes sense?
Yeah. Makes perfect sense.
Okay, cool.
So the dark side of the moon is not as mysterious as Mulan had us believe.
It actually is, because all the mare which didn't reach the surface are just like frozen in time there. It's kind of creepy that there are those mare which never reached the surface. For me, it's kind of sad, They kind of wanted to go to the surface but never reached it because it was so thick and so cold. Those poor mare.
You know this video, the lava song?
Yeah.
I Lava You. It reminds me of this song. It's so sad. And then it's beautiful.
Yeah.
But it starts so sad.
Yeah, exactly. So these
Look
are
it up. We'll link it. Look it up.
We will link it. It's a very beautiful song, which is also very fitting because we record this podcast very close to Valentine's Day. So
true. You won't hear it until very much later, but
yeah. So
you can always re-listen.
Yeah, you can always re-listen, and remember, if you have someone in your life to say I love you, take the chance and say I love you.
Don't wait.
Yeah. And moving on, we have highlands, so the Ferroan anorthosites. And like I said, these are the oldest type of rocks and make up 80% of the highland crust. And this majority of samples are from the Apollo 16, like also I already mentioned. So this is the Apollo mission, which actually provided very significant impact for scientific community. This brought us huge evidence for the theory that I already explained, which is the lunar magma ocean. So after formation of the moon, we think that the moon was molten, either fully or partially molten. So it was like an ocean of magma. You can imagine it like that. And then it slowly cooled down. And when it was cooling down, there's this certain type of mineral, which is called plagioclase. And this mineral is lighter than the magma. So it starts to float like icebergs on the ocean. And this is how the ferroanorthosite crust was created. Oh, this is the leading theory for now. And then you also mention the other feature, right? The craters. So when we look at the moon, the craters are more than just scars. They are like timestamps written in the surface. And now, Tika, can you describe what you see? Because I've sent you this one specific crater. And they are the features which you also already mentioned, which are very, very interesting. And I love that you said it already at the very beginning.
I'm sometimes surprised myself with these observations.
Yeah, you're very good with it.
Yeah. So this one crater, I'm very glad you added an arrow because I would have not seen it otherwise. It's tiny in comparison to the rest of the moon and to the rest of the mares we just discussed. It's in the white spot, the whitest, brightest spot of the moon, and maybe that's the case because it's closest to the sun. I'm not sure. I'm just assuming here. But it seems like a lot of stripes are radiating from it. It's like a center of these stripes, like a spiderweb center.
Yes.
And you're looking very happy right now. So yay.
Oh man, I really like your observations. You're really good at catching all those nuisance And these are very important observations. So yeah, what I showed to Tika right now was a photo of moon with a big arrow pointing to Tycho crater. And Tycho looks very ancient because, of course, it's on the moon, but it's actually very young. It's about 100 million years old. That means that when the impact happened, the dinosaurs were still walking on Earth. Yeah. Can you imagine being a dinosaur and there's this massive impact on the moon? It must have looked amazing.
Yeah, but it's the only thing we know from dinosaurs. All these pictures show them looking at giant impact. So to me, it makes sense.
I mean, man, the dinosaurs were living in the best time, all the impact happening.
Mass extinction time. But yeah, great otherwise.
Good times, mass extinction. Yeah, and the spider net that you mentioned is like rays. They are actually called rays system, and they are created when the impact hits and it ejects all the material out of the crater and they fall into the specific rays. And the system is so bright because the space weathering has not darkened it yet. That's why we know that this is a very young event. And of course also crater dating. And moon has no atmosphere like we mentioned, or plate tectonic to erase its past. So scientists can use the crater density to estimate the relative age of different regions. So it's like the more craters, the older the surface. Makes sense. Yeah. And many of these impacts date back to a period known as Late Heavy Bombardment. And around 4 billion years ago, our young inner solar system underwent bombardment by asteroids that carved huge basins in the Earth's moon. So all those big basins, we think they are coming from this heavy bombardment. And it happened due to the change of orbits of the giant planets like Jupiter, Saturn, Uranus, and Neptune. Go back to listen to our episode 4, part 3, guys, to know more about these gas giants. And this event threw asteroids from the asteroids belt into this array and sent those leftover pieces of the solar system formation to start crushing into the inner planets. So it was rough time to be alive. And
Isn't it always?
Is it always? I bet housing prices were not that crazy back then. And
climate was warm enough to live outside.
Yeah. So while the Earth's surface has largely erased this violent era, the moon preserved it, and so the same impacts may also contributed to the late veneer on Earth. So of course, you can estimate that the amount of material which impacted the moon, it kind of, you can scale it up to the size of our planet, so it also entered our planet. And we actually can trace these events back if you check into Earth geochemistry, which I think is quite interesting. But the late veneer and the late heavy bombardment, it's not scientifically, it's not set in stone. So we still debate over it. And there are more studies which are done, and scientists argue that the lunar basins are generally extremely difficult to date and could be contaminated with material from impacts which are formed from other basins. So it's generally very messy, it's rubble, so you kind of sieve through a rubble of ancient impacts trying to make sense out of it, which is not always so straightforward. And this debate continues today, with scientists proposing that the late heavy bombardment was more gradual, it was not like just one big event, and such spikes could also just not occur at all. So the decisive answer could be provided by future lunar missions that could return more samples to our scientific labs.
I think it also depends on what timeline we discuss as scientists, like heavy bombardment over millions of years or heavy bombardment over hundreds of thousands of years makes a big difference in science.
Yeah. You know, for us also, if we say like it was over a short period of time, we are not talking about days. We are talking about thousands of years, right? So let's say the heavy bombardment or the late bombardment is placed like 4 billion years ago, but it spanned across millions of years.
Yeah.
Yeah. And then, let's talk of the future, because we are living in very interesting time. Because I don't know, Tika, if you know, but we are going back to the moon.
Yeah, I knew. I heard on the news, actually. I'm not sure what the core goal is of this mission. If I think back to this episode, it might be because Trump is just trying to put a flag in anything other than Greenland because he failed there. But explain to me, let me know.
Yeah.
What are we doing?
So we are entering a new era of space exploration. And like we mentioned at the very beginning, Apollo was about getting there first, not necessarily with scientists. And Artemis is about staying. So NASA Artemis program aims to return humans to the moon and establish a long-term presence at the lunar South Pole and prepare to launch to Mars.
Oh, that's insane.
That's already very advanced planning, because there's a sequence of mission. The Artemis 1 mission was already successful. And I was like just trying if our technology could sustain the next missions and check if after 60 years of not going to so far out of, Earth orbit, if we can still do it. We can, spoiler alert. Then Artemis 2 mission is targeted for 2026 in March. So hopefully when we will release this episode, we will have already some news about that. I think we definitely will follow up on Instagram. So please check our Instagram if you did not do it yet. And Artemis 2 mission crew will fly around moon, so they will not land. They will not touch the lunar surface. This is gonna be the Artemis 3. So Artemis 3 aims to land astronauts on the lunar surface. However, it's still very important because the Artemis 2, the one which will be in March, is the moment that humans will leave Earth orbit for the first time since 1970s.
So exciting. I'm sure we will make sure to comment on this historical event and achievement when we get to it. So you don't have to wonder what on earth is happening.
Because we gotcha, guys. We gotcha. I think this is a perfect moment to just wrap up, because we covered everything perfectly on time. Tika, you were just too smart for this episode. We don't have to split it into parts, because you spot the Mari, you spot the highlands, you spot the craters, you got the rays. I'm absolutely amazed. So to our beloved listeners, thank you for spending time with us and joining for another little escape into space. We hope this episode kept you curious and inspired, and maybe even made your evening feel a bit more magical. And if you enjoyed this episode, leave us a comment, a like, a follow on Instagram, Facebook, Spotify, or wherever you're getting your podcast, because every single message truly means a world to us.
And the moon.
And the moon. So until next time, stay curious and keep asking yourself,
what on earth is going on here?